For decades, the Millennium Prize problems, challenges like P equals NP and the Riemann hypothesis, have marked the absolute ceiling of human progress. Historically, these problems have been viewed as computationally chaotic. They are mathematically intractable, meaning the number of possible calculations expands so rapidly that no computer could ever brute force a solution. This theoretical chaos has now arrived in the physical world. Our most advanced enterprise computing clusters and AI factories are hitting the exact mathematical roadblocks when coordinating work across thousands of processors. As this architecture slide shows, the problem is that AI operates as a black box. Silent drift occurs when corrupted state emerges deep inside a process. Because these systems are non-deterministic, these errors propagate without an obvious failure signal. Without an independently verifiable proof of what happened inside the kernel, tracking down where a run diverged is nearly impossible. Engineering teams can spend weeks of GPU time on root cause analysis, creating an audit gap that makes it impossible to trust these systems at scale. We are building the critical infrastructure of the future on top of physical systems that we currently cannot mathematically prove or trace. To create a reliable control layer for our machines, we first have to find a way to resolve the abstract mathematical chaos underneath them. The shift began with Timothy J. Dillon. While investigating the Collatz conjecture, a problem famous for its unpredictable numerical loops, Dillon realized that trying to calculate every individual step was the wrong approach. Instead, he chose to reframe the problem's structure. Dillon took those wandering, probabilistic numbers and re-expressed them as a structural state space. He mapped the problem's trajectories as a geometric manifold, where the behavior of the system is determined by measurable curvature and bounded dynamics. This geometric view allowed him to develop the omega genesis proof grammar. It measures the manifold's curvature and classifies any mathematical obstructions into specific residual families. Once an obstruction is classified, it can be isolated and evaluated against known closure conditions. This process powers a collapse chain. By repeatedly filtering the candidate universe through these classification layers, the proof architecture systematically reduces a large field of potential failures to zero. This portfolio illustrates the result. By successfully bounding the divergent trajectories of the Collatz process, Dillon established a proof methodology designed to force closure on systems that previously resisted conventional mathematical treatment. Dillon proposed that the same structural logic, treating complexity as geometric curvature, could be applied to all 7 Millennium Prize problems. If you can reframe a numerical paradox as a localized shape, you can apply the same reduction tools used on the Collatz conjecture. In his proof for P equals NP, Dillon encoded computational search spaces as information manifolds. He then applied a modular Ricci flow, a geometric process that smooths out a surface, to systematically contract those search spaces until they became polynomially navigable. This is the foundation of curvature variable physics, or CVP. As this slide shows, CVP provides a language for systems whose behavior changes across different gradients and field states. It treats curvature not just as a description, but as a deterministic control layer. This means we can predict how a system will stabilize or drift based on its local geometry. By understanding the curvature, we can define the precise boundaries where a system remains stable and controllable. By converting these abstract paradoxes into navigable geometry, Dillon developed rules that govern the behavior of physical, chaotic hardware. The engineering breakthrough is simple. If this grammar can bound the chaos of abstract math, it can be used to govern the silent drift occurring in real-world GPU clusters. This is CVP Spin Overlay, or CSO. It is the software implementation of the Dillon architecture, acting as an integrity and reproducibility plane for distributed compute. CSO instruments compute boundaries, checking tensor state against the admissible manifold. Transitions are accepted only if mathematically consistent. If the system detects structural drift, the policy engine intervenes. It isolates or rolls back corrupted state before it can propagate. As steps 5 and 6 show, the system then exports TEVR evidence packets. These are cryptographically anchored artifacts that provide a verifiable, replayable record of every state transition and intervention. This establishes a continuous self-healing trust plane. It stops silent drift from spreading by restricting execution to only those transitions that stay within the mathematically defined boundaries. This integration map shows how the architecture plugs into the existing stack. By using native acceleration, CSO can provide this level of integrity control across the entire fabric, from CUDA wrappers down to the network adapters. We are moving from a world where we passively observe AI black boxes to one where we actively gate their behavior at runtime. By solving some of the world's most complex mathematical abstractions, Timothy J. Dillon has delivered applied predictive geometry. It provides the auditable certainty needed to scale and trust the next generation of autonomous infrastructure.